return to the carry save headers. I know you like me to tell you stories about dogs, but then let us assume I have these two numbers. If I want to do an addition, then I will apply a full header here, which will give me a 1 and a transport. The transport will be absorbed here, or give me a 1 and the transport will be absorbed here. No, 1 plus 1 is 2, sorry, 0 and the 1. I'm not, okay. There will be no transport here, but I have to wait for it because I don't know whether or not it's a transport. Then this one will give me again a 0 and a transport. This will give me a 0 and a transport. Then this will take 1, 2, 3, 4 full header delays. Now instead of bringing the transport to the next location, I will store it in an explicit way. Then this will give me 0, 1, this will give me 0 and no transport, this will give me 0, 1, this will give me 1 and 0. Then I am not really computing the number, I'm just rewriting it as 2 numbers. Now I can do that essentially for 3 numbers because the full header has 3 inputs. Then I did the calculation in the delay of a full header, not in a delay which depends on the width of the operands. And that's the beauty of this carry save header. It's postponing the propagation of carry. But eventually I will have to do that propagation at the end of the calculation. And if I have to add n numbers, the first iteration I can take 3 of them, then they will participate in such a carry save header, then each iteration I take a new one because the previous value will be stored as a sum and a carry, plus a new value can go in the full header again. And again until at the last iteration I have 2 numbers, which are now sum and carry, which I have now to really add with a carry propagate header. And this is making each iteration, but the last one, very fast. And that's the key behind making multiplication fast and making multi-operand addition fast. Now here you have a structure which is doing addition using carry save headers. And this is a 3. Then I have 7 numbers as before. And while before each stage took something which was linear or logarithmic in the dimension of the operand, now each stage takes 1 full header delay. At the end of the calculation, I have these 2 numbers, and in here I have to place a carry propagate header. Then the delay of this scheme will depend on the depth of the tree, which is logarithmic in the number of numbers, operands that I'm adding, but now the factor is 1, because it's a full header delay, plus this. And I can even play this trick in a serial fashion if I want. Then if this is too much for me, and it's too expensive, I can go for a serial approach. Then I have only 1 carry save header, and I'm feeding back, you know, the sum and the register from the previous accumulation, plus a new number, and I'm accumulating. This is certainly slower, because it's kind of linear in the number of operands, but it's not that slow, because each and every iteration takes 1 full header delay, plus the setup time and the hold time of the registers. I said that probably before, but when I store something in a register or in a flip-flop, that value has to be stable before the clock is coming and after the clock is coming for some time. Otherwise, the sampling in the register will not be, or there is a chance that I will sample the wrong value. Then the cycle time of this is determined by 1 full header plus hold and setup time for these registers. which direction should I go? Should I go for this or should I go for that? If you get such a question, how do you answer it?
It depends on the situation.
How can I compare two such approaches? That's more my question. Sorry?
Resource usage.
Resource usage, and how do I know what the resource usage is?
So here we see one carry save adder and one carry propagate adder, and then the other one, each level, it have a few of them, so
Sure, then this is better, right?
quad resource, yes.
Yeah, but it's slower.
It's
on your end, Andres.
On mine?
And
No, what, I still have a problem because I don't know where to put the accent, on speed or on complexity. You know, when I evaluate a design, there are metrics, okay? And what we are facing now, it's a kind of chicken and egg problem, if you want. If I look on area, this is my guide. If I look on delay, this is my guide, and I cannot make any kind of decision. And for that reason, we have what are called combined metrics. And I will take the design which has the best figure of merit in terms of area delay product. Then I will multiply the area of this design with the delay of this design, and the area of this design with the delay of this design. And this will capture both aspects in one metric. And the one which has the smallest number is the best one in terms of resource utilization versus delay. This is capturing the efficiency of the utilization of the resources. And in my calculation, I can draw parts which are common. Then this and this are common. They don't matter. They are the same in both designs. Then I will just concentrate on this part, and then I can see which one is more effective. And that will depend on many things like technology also. And this is one metric. There are metrics which are like energy delay product, energy square delay, area square delay. And those metrics are trying to capture the figure of merit of a design from more angles while giving kind of more priority to one parameter. Then if I say area square delay, it means that the area is more important than the delay. But if I say area delay square, then delay is more important. And those are signals that I get from the application. I know in my application what should be more important. Okay. Now, this is an example on how I make the reduction based on carry-save adders. Then I make a tree which does not look like a tree, but it's a tree from the logical point of view. Then I start with my numbers. My numbers, remember, are 7 operands. Each of them, it's a 6-bit operand. 7 and 6 are just, random values. Now, what do I want? I want to make a reduction from those 7 numbers to 2 numbers while applying carry-save addition technique. Then I am following the previous slide from the tree construction point of view. But this is looking more like the layout of my circuit, and it looks, more compact, assuming that I can place the dots, which are the input operands, in that way. If they are coming on the geometry of my circuit in a different way, the layout would not look like that. Now, I look at the first level. I have 7 times 6 dots, okay? Each dot is in a certain position. Then I have to be careful to preserve the weight of that position, because dots which are here in the first are 2 to the power 0, while dots which are here are 2 to the power 2. But when I process them, I do that independently of the weight, because locally in the column, the weight does not matter. But when I'm rewriting this matrix, at the next stage, I have to do it in a proper way. Now, I will try to process as many dots as possible in parallel. I know a full adder can take 3 dots and rewrite them as 2 dots, one in the current column and one in the next column. And what do? I see those dots per column. I have 7. Then I can apply 2 full adders for each column in parallel. And this will happen 6 times. Now, the result of those full adders will be available in the same time, because inputs are available in the same time, they are processed in the same time, and the result will be available. I have a very nice structure here, which I will kind of damage going down, but there is no way to make an omelette without, breaking the eggs. Then I have 2 full adders here. Each of them will report a sum bit and a carry bit. In order to make this clear, I link them with this line. Then this and this are the outputs of this full adder. This and this are the outputs of the second full adder. This is a dot which I could not do anything with in this level. And I am doing that 6 times. Now, what you see is a different kind of representation is in here. And this representation is telling me the following. This is the column position. And these are the number of dots that I had in that position. And you see, I started with 7 per each column. I applied 6 times 2 full adders according to what I did here. Then my cost in here is 12 full adders. What I obtain is this pattern. Now you see I have 3, 5, 5, 5, 5, and I have an extra column. I grew a bit. I'm absorbing values and I have to grow. Now, the second level, did I arrive to 2 numbers? Not yet. My target is to get to 2 numbers. What do? In here I have 3 dots and I'm very happy. I cover them with a full adder and they give me a sum and a carry. In here I have 5 dots and now I can do 2 things. I can take 3 dots per each column and report to the output. Or I can also say I want to push harder. And then I take 3 dots for full adder here and I take also those 2 with a half adder. This will make an investment which may or may not pay back. We'll see later on that this most likely will not pay back. But this is moving the compression because it's rewriting the dots from that position into that position, then kind of extending the number. We won't do that now. We just say I have only full adders. I cover with full adders whatever I have. And now there are 6 full adders, which are those guys in here. This is kind of bigger than this, but they are the same. The distance between points is not relevant. They all generate output. And now you see, I started with a maximum height of 5, and I end up in 4, the maximum height of the column. And this is my new structure. And I applied 6 full adders, and this is my new structure. I already have a bit for the output. In the least significant position, I have a bit which will not participate into the calculation any longer, neither in the final carry propagation. Now I have 4. I apply the same trick. I cover with full adders whatever I can cover. I apply again 6 full adders and I obtain this new value. Okay, and this is now my pattern. I grew with 1 more position. And this will be my last step. And in my last step, what I am trying, I can do many things, but I will skip with the straightforward solution, which is I will leave those as they are, even though I could compress them. If I apply here a half adder. This will result in a dot here and a dot here. Then I will have 2 bits for the output already. But I won't do that. Then I put full adders. Each of them will report some kind of things. In here, I put a half adder, and that will report that. And now what I have is, I have a solo bit, which won't participate, and I have 2 numbers, which I now can add with a carry propagate adder. And I will use a 7-bit adder. Now, this is more suggestive because I see the way I interconnect things and the way my matrix is evolving. This is telling the same story, but it's a bit more, let's say, it's not that intuitive because I don't have the figure of it. If I get used with that notation, I understand it also. Now, when I ask you in an exam question to do that kind of stuff, it's better to try to do this. I won't give you millions of bits by millions of bits. Then you can draw it. That, it's also okay, but it's more compact, but it's kind of more prone to error. Now, I could win a bit if I would have applied here a full adder. Because when I apply here a half adder, not a full adder, then I will get a solo bit here, and in here a dot, which means my final adder would be 6-bit adder. Then by making a small trick without increasing the delay, I am decreasing the delay of my final adder, which even, it might be carry, ripple carry, or carry look ahead or whatever, but making a change from 7 to 6 may make a difference, or may not make a difference, depends on how I do it. If it is a ripple carry, it will certainly make a difference, because it's 1 ripple level less. If I do other things, it may not. Are we clear on the way I can do addition of n numbers by means of carry save addition? In a number, I will call those iterations, but they are not really iterations because they are levels in the reduction. Now, you saw I started with 7, I end up in 5, 4, 3, 2, 1. There is a kind of regularity in this, the number of columns, of the numbers of rows that you get in the column. And this is determined by the power of your compressor. We call those full adders also compressors. If I could use a larger capacity full adders, that I would call a population counter, things will look a bit different, and we'll discuss about that further. But in most of the implementations, when we deal with this kind of multi-operand addition, we rely on full adders because they are very good in practical implementations. Okay, now this is a kind of the same story. Now it's drawn like a tree. Essentially, this is related to what I said. It's the number of levels that I need in order to get from n inputs to 2 outputs. Then I make a tree. It's a tree, right? And the power of that tree depends on the power of the reduction element, which in my case is full adder. If I apply a full adder and I use some kind of formulas which are proper to trees, I can get this table, which is telling me how many inputs I can reduce in a number of levels. If I have 2 inputs, I have no tree, because 2 inputs I already have the result. If I have 3 inputs, then I will need 1 full adder because this will do 3 to 2. If I have 4 inputs, I cannot do it in 1 level. I will do first 3 to 2, and then another one with the 2 plus the reported one from the previous. Now, for larger than 4, then if I am between, let's say if I have 6, I need 3 levels. If I have 9, 4 levels, 13, 5 levels, 19, 6 levels. If I am in between, I have this kind of things. Then depending on where I am, I can get my reduction also to not to follow exactly those kind of beautiful numbers. And if I get, let's say, with somewhere between those numbers, this will not allow me to jump to the next place. This will probably move me into this and will give me extra things to do. Then, in other words, what I'm saying is that given this structure, regular structure of reduction, which follows this 3-to-2 reduction pattern, whenever you have a random number of inputs, you have two strategies. You reduce whatever dots you see, then whenever you have 3 dots in the same column, you put a full adder on them. Doesn't matter what you obtain, then you do a greedy approach. Or you say, will it give me any kind of benefit to do that? Will that bring me some advantage or not? Because some of those reductions will place you between those levels and will not bring you any kind of advantage. And then you spend hardware without really getting the advantage. Now, if I change the counter that I use, those numbers will change. But, you know, because this is related to 3-to-2 compression. If I have other compression, that will be the formula. Okay. Now, based on that observation, I have 2 approaches. One is called Wallace and the other one is called Dada, from the name of the guys which came with the approach. Wallace is the greedy one. Wallace is saying, whenever I see 3 dots, I apply a full adder. Dada is saying, sometimes it may not be good to apply the full adder because this will not give you any advantage. And the Wallace is plus or minus what we had before. And you see, he's bringing us from 7 to 5. Which is kind of, you see, in between those levels. Those are the beautiful numbers that I would like to get on. Then I started on 7, which I'm here. Then he's bringing me to 5, which is in between. This is not really an advantage. And he's saying, okay, instead of applying 12 full adders at the beginning, I will apply only 6. Then I will compress from 7 to 6, and then I follow the normal compression. 6 to 4, 4 to 3, 3 to 2. Then I'm following now the maximum number of dots in the column according to that beautiful table. I did not increase the number of the levels of reduction, is the same number of levels. And I saved half of the cost on the first level. It looks good, right? But there is always a price to pay. Because I didn't do that, I may get some problems later on in here. In this case, it's a beautiful example. It's no difference between the approaches. But what you get is sometimes this is cheaper, and you may get a price here, an extra price, because this may get wider. Now, if you deal, I don't know why Parhami made that choice. It doesn't look to me like a good example. It would have been good to have an example where you see the difference. But do you get the difference between the 2 approaches? I have one goal. My goal is to make the reduction as fast as possible to 2. I have full headers to rely on, and I apply them in parallel. And one, it's a greedy approach, which is whenever I see 3 dots, I don't think about consequences, I just apply them. And the other one is saying, will that make sense to do it? Will that place me in a golden number in the table or in between? If it's placing me in between, maybe it doesn't make sense to do it. Eventually, because this is less aggressive on the extension, on the propagation, on the rewriting of the numbers, you may get here with a wider full header. Then, practically, this is what we know. Those are kind of old proposals. And I'm not sure if Dada is still alive. I know the guy, and we've been in conferences, and he was, let's say 10 years ago, he was very old.
Yeah.
Then most likely now he should be older than 80. But he might be still okay. The other guy I never met. And the first guy is an American, and Dada is an Italian. He was professor in Milan. Okay, now, are we okay with this? Okay, brilliant. Okay, what I see here is a small optimization. And what is this small optimization doing is I'm saving things. Okay, if you look at this scheme, this is again Dada's approach. And what I'm doing is, because my full header in the first position in the header, in the carry propagate header, has 2 inputs and a carry in, which I'm not using in the previous case, I would like to use it here. Then I will not reduce those 3 to 2. I don't have to. Here I have anyway a ripple carry header. And then I save here something, and I utilize here a carry propagate header where I'm utilizing the input of the least significant bit also. It's a simple trick which is saving me something, and now you see there is kind of small difference between Wallace and Dada. I have less full headers, but I have more half headers. Which means that by creatively combining full headers with half headers, I can get into more optimized solutions. What I have to be sure is that I'm not increasing the number of levels. Then when I'm postponing reduction, I should not increase the number of levels, because then I will have an extra penalty in the design. Then if in here I have an extra level, then it's not a good solution. As long as I keep the same number of levels in the reduction tree, and I am trying to minimize this, I'm getting into a good solution. Okay. Now we were discussing about that scheme in the context of full headers, which we also call 3-to-2 counters. And those in general are called population counters, because they take n inputs and they represent the number, the population in that inputs, in the output value, which is now logarithmic in n. Then if I have a counter which can count from 0 to 7, I need 3 bits in order to represent that value. And this is called the 7-to-3 counter. If my technology can implement that directly in one stage like a full header, my tree will change and the compression will be a lot more aggressive. However, what we do most of the time is we build larger counters based on full headers and half headers. This is essentially here what we have. It's a 10 to 4 counter. This is the design of the 10 to 4 counter. Then this is assuming 10 input bits. In the first place, it's taking groups of 3, applies full adders, then it's a first conversion, then this is the first compression, are these 3 full adders, which are here. They are generating carries and sums, and I have this result, where I have those 2 full adders, and then I have this carry propagate adder, which is a half adder, full adder, half adder. This is the implementation of a 10 to 4 counter. Now, if I can derive a reduction tree based on that, which is more efficient than a reduction tree based on a full adder, I should go for that. In number of levels, this will be more efficient for sure, but I have to magnify, the inside of this implementation and count the real, levels here. Now, there are different kind of things, and in Boolean, essentially, it doesn't matter where you go, you kind of end up in keeping the full adder stuff. But there are other approaches which could do that calculation in a nicer way. Okay, one of them is called threshold logic. Okay, it's built up on the neural networks model. Okay, maybe you heard about McCulloch-Pitt neurons? No. Okay. Have you heard about neural networks? Yeah, okay. Then they assume that this is a beautiful neuron. This is the axon. These are synapses, connections with other neurons. And here is the soma of the neuron. And depending on the compound action of the synapses connections, the neuron will fire or not, which means the neuron will send a signal on the axon, which will now connect to other neurons. Now, this is kind of what we believe about neurons. There are other models as well. And basically, the mathematical model of this is saying that the output of the neuron is signal of sum of xi w I minus, this is the excitation threshold of the neuron. These are the inputs, the zeros or 1 coming from other neurons, and these are synaptic weights. When I do neural networks, what I'm doing is I'm adapting these synaptic weights in order to give the right answer to the problem. But I can use such a trick with fixed weights and get implementations of Boolean functions. Then this is, if I assume learning in this system, I'm getting neural networks. If I assume that those are pre-computed and fixed, I get what is called threshold logic. And now in threshold logic, I can compute that kind of counters in a more effective way, assuming that I have some hardware to build those. Then larger counters will make sense in threshold logic. They do not really make sense in Boolean logic, but who knows what the future will bring us. And even in standard technology today, such an approach might be useful from time to time. I would rather skip those because somehow this is making the story even more complex. Because this is a counter, it's a reduction tree where you have inputs coming from the top, but you also have inputs which are accumulated at each level of the tree. And it's kind of too early to discuss that. Also this. Then you can safely assume that I will not ask you about those slides, except if I will come back to them eventually, which most likely I will not. Now, we had 3 to 2 counters or 7 to 3 or 10 to 4 or whatever, n to log n. Those are called population counters. But the technology can allow me also to build different kind of counters, larger, wider, whatever. And here we have some example of generalized parallel counters. I can use those two in the reduction of that matrix. The bottom line is to have nice implementation of those, which let me beat the standard approach on my problem. Okay? And when I see, like the first one, this is a 2-column counter. I symbolically say that it's a 5-5-4 counter. 5 means that I have 5 dots in the column, and 4 means that I have 4 dots in the output. Then I have 2 columns. Now, as opposed to the previous case, each column has a weight, which is different. Then this is 2 at power 0. This is 2 at power 1. Now, when I add the number, in the best case, this will be 5 plus 2 times 5. Then my number will be maximum 15. Then I will need 4 bits to represent it. And the beauty of that is that this allows me to do what is called block save addition. If I partition my operand in this way, in blocks like that, you see that the carries out of this block are not going further than the next block. Then I can do things in parallel. I will have bits in my current counter position and some carries into the next one, but not any further. Then I will make a reduction. This is called block save addition. And sometimes this can be advantageous. I can also have that kind of counters, 2, 3, 3. This is the most significant column of the counter. This is the least significant, and this is the number of bits. Now, those are useful. As I said, if I can implement them in a nice way, they may result in beautiful implementations. Now, the question is, how do I implement such a counter? I will use something like here. That I now have a different kind of dot diagram, and I will still rely on my full adder and half adders. Also for those. The bottom line is whether or not I win. Now, this is another type of counter which is making a step forward. And it's allowing for what is actually not a normal reduction. Whenever I have n inputs, the maximum value is represented on log n bits. There is no way to do otherwise. Those are called n to 2 counters. And the name is a bit kind of intriguing. I take n bits, n dots, and I represent the result as 2. Now, I cannot, except if I do something. And that something will be to have communication, then to give transfer to the next position. Then I take those 4 bits. Okay, they are in this column. And I am trying to do a compression. I need 3 bits to represent the maximum value. What I'm doing with those counters, I'm saying, no, I just need those 2 bits. I will do some kind of mumbo jumbo, some kind of magic to conserve the value while producing just 2 bits. Now, how can I conserve the value? The value I can only conserve if I push some carries to the next position. But when I hear about carries, it's kind of against the concept in counters. My idea about counters was that I was generating dots, and I'm not kind of making any carry propagation. The beauty of those counters, which is suggested here, is that when I am in in a certain column position, and remember I am in such a big matrix, and I'm applying the counter here. This will take a lot of inputs and will generate two outputs. In order to preserve the value, some transfer bits should go in the next columns. Now, if I generate transfer bits in the next columns, this is like I'm representing them on log n outputs because they will be considered later on. This is not what I want. What I want is that those transfers are not delaying the calculation, but are considered in this moment of the calculation. And how do I do that? By designing those counters in such a way that while, like in here, they take n inputs, they generate two outputs. One is the sum here and a carry into the next position. This will be the output. But they generate some carries into next positions, 1, 2, or many, depending, which are contributing into the calculation without increasing the delay. Then, this is my counter. I'm taking here n, and I'm taking here n. Let's say, let's simplify things. This is 4, this is 4. I'm generating a sum and a carry here, a sum and a carry here. Now, normally speaking, I have here an extra bit to generate. This is 4 to 3 population-wise. What I should do is split this counter into stages and do some computation which determines a carry which will go in the next position or in maybe another position after the first stage and contribute into the calculation of the second stage of the neighbor. Then first, second, second. The fact that I am generating this to my neighbor in the same time when it is required and not here at the output to be considered in the next stage, it's actually hiding the propagation because this is not real a propagation that I can see. It's not increasing the delay. If I would inject it here, then it would be a real delay because it will be considered in the next stage. Now I can make that split in more things. And what I have to be sure that I am generating, here I have 3 types of carry, Phi1, Phi2, Phi3. Phi1 is going over 1 stage, Phi2 over 2 stages, Phi3 over 3 stages. Then my counter is split in 3 stages. And then I have the first level, which is considering, my local inputs. I have the second level, which is considering some of this and the carry coming from the previous guy. The fact that it's coming from the previous is not increasing the delay because it's calculated in parallel with this. And I'm generating a carry to my next position. And let's say I'm getting some calculation again. I have 3 stages now. And I'm doing, for this one. And then I'm done. What I did is in one stage of compression, I did more than n to log n compression. I don't really have carries in the sense that they are propagating, they are waiting for each other, but I have transport between the columns which are taken into calculation in that stage. Okay? And this can help me a lot. And now I have to choose, how those carries are going in order to preserve the value. Because you see, I have my input into the counter, which is the n inputs plus some carries. And that one should be smaller or equal to 3, which is the maximum number I can represent with my 2 outputs, current and a carry to the next, plus carries into the next position. The next, the second next, the third next. And then now I have a lot of freedom in making the design of such a counter. This will result in a faster compression in the network, then I will have less levels. I have carries, but I will call them horizontal carries, because even though they travel between columns, they do not create extra delays. Okay. I'm already late. I have to close the shop. I think there is one more example. Yes. Okay, there are 2 slides about that, or 3 slides, which we'll discuss Monday. Yes, what do you want?
If the carry is propagated from the last state.
From the last stage,
State.
where?